Okay, so we're up and running. Here's where we left off. We were talking about arc length and such, and so we actually finished this section. I guess I was on the wrong page. Okay, so here's where we left off. So starting with 3.3 about vector fields. So this is a new kind of mathematical construction. It's a completely new mathematical object. Well, in a sense, in some sense, nothing's new. So this is as a definition, what a vector field on Rn is a function from Rn to Rn. Now, it turns out there are different kinds of functions from Rn to Rn that we're going to care about in this course. What distinguishes a vector field specifically among these kinds of functions is mostly how we look at it. And so the way we represent such a thing, this vector field, we represent the input as a point, such as, for example, right there, right? We have x. The input. What's going to be the input to this function? We think of as being a point, and then what we think of as being the output, what is the output we think of as being a vector. And specifically, of course, we represent vectors with arrows. Specifically, we represent it with an arrow whose tail is at the point. At that point, that was the input. Okay, so this is the kind of picture. So when you're talking about a vector field on Rn, you're talking about basically a picture kind of like this, which we make algebraic and precise by way of a multivariable function like that. So that's an example of a vector field. Now you'll notice this is a vector field in two dimensions, right? There's two dimensions of points because it's in the xy plane. There's two dimensions for the vector field because it's got to be a vector in the xy plane, right? But there is such a thing as a vector field in R3 that would look like this. And you can see for every point we get a vector. Right? So that would just same basic idea, just R3s instead of R2s. Okay. Now, a couple things to say about this. One, why would we be interested in such a thing? Right? What's the why are we doing this? Right? Reasonable question. Why we're doing this is because this is exactly the mathematical object that we need to represent lots of real-world phenomena. Short answer. Right? This is just the perfect tool for representing several things. For example, fluid flows. Right? You can almost kind of see that happening. You look at this picture, right? And you think about, doesn't it just kind of conjure an image in your mind of, it looks like there's a fluid kind of flowing to the right and slightly up, right? Something like that. So, in fact, vector fields are how we describe fluid flows. And again, the real world, full of fluids, whose flows we need to understand. Right? So that's a great tool for this. Okay. Next comment I want to make about this before we go on is what is this picture that we're looking at? Remember, we've spent a lot of time talking about the relationship between algebraic objects, functions in particular, and how we represent them, geometrically. What kind of pictures do we draw? And let's go through the list. We've talked about graphs, not to be confused with level sets that we've also talked about, not to be confused with parameterizations, right? That's a completely different from graphs and level sets relationship between algebra and geometry. Oh, I like what I like to call the literal picture of a function. That's 4. This picture here is none of those 4. This is number 5. Right? Again, a completely different kind of a picture. So I emphasize this because, again, a lot of students don't take this seriously enough, and just try to take whatever calculus, algebraic, representation of calculus they see, and try to just visualize it on whatever picture they happen to be looking at. And this is doomed strategy, right? It will not work. What calculus looks like on a given picture depends massively What kind of a picture is it? Okay, so please do keep that in mind. Do not, please think that they're, like if you look at some sort of derivatives that you might write down of this function, that might, for example, represent slopes here. Nope, it doesn't. Right? Totally different picture, totally different understanding of how calculus is represented geometrically. Okay. And in fact, you might say chapters 6 and 7, large parts of chapters 6 and 7 that we're going to actually get a glimpse of later today, hopefully, if I can keep things moving along, if I don't digress too much. The calculus of vector fields, not to be confused with the calculus of graphs, calculus of a level sense. We're going to talk about some of the calculus of vector fields today, later today, and again, that will be one of the primary points of chapter 6 and 7. Okay. All right, so lots to do with vector fields. A couple of examples. This is what a constant looks like. Notice that our, for an input point x, y, we've got an output formula here, 2, 1. And notice that is a constant. Right? So this is what a constant vector field looks like. Now, is that a horizontal line? Or is it a bunch of horizontal lines or something like that? No, absolutely not, because this isn't a graph. Right? So again, make sure to not conflate. Don't use your geometric intuition that you have from graphs to try to gain some geometric intuition for vector fields. It doesn't work. It's wrong. Right? So this is what a constant looks like. And I hope this makes sense, because you notice that it's the exact same field vector everywhere. Those are all the exact same vector. Same direction, same magnitude. They're different arrows, of course. Arrows have locations, but the vectors that the arrows represent do not have location. That's all the same vector. Okay. All right, here's another one, another pretty standard example, and that is, what if the point x comma y is the field vector also? What does that look like? And the way to see this, in my point of view, is to remember that when you have a point, as we do here, xy is a point. Okay, we can say we're going to view it as a point, and it is a point, and that's fine and all, but there is the associated position vector. And when I say that the field vector is a vector that is the same as the input point, then I'm effectively saying that it is the position vector. So this green position vector for xy, this blue vector xy, same vector. Again, they're represented by two different arrows, because we have two different conventions for how to draw the arrows representing said vector, but same vector. Okay, so now having made that observation, we'll look at this picture and notice that whatever point you happen to be looking at, right, the field vector points away from the origin, and the farther the point is away from the origin, the longer that field vector is. And so with that interpretation in mind, you get a picture that looks kind of like this. Does that make sense to everybody? Everybody happy? By the way, you'll notice that the argument that we made to deduce this picture and the argument that we made to deduce this picture, totally unrelated. Right? They're different vector fields, and different clever observation happened to help us generate that picture. There is no single automatic, turn the crank method for drawing pictures of vector fields. You have to look for something that stands out and think carefully about how we draw vector fields. This process we have for drawing vector fields, and think it through. And it's a very creative thinking kind of process. It's not a mechanical. It's not an algorithm. Okay. All right. So let's see here, moving along. Yeah, this is an interesting one, pretty unexpected. You look at this, it seems like it ought to be, it's linear. Doesn't this seem like this ought to be like, being as it is, literally a linear transformation? Shouldn't it be like straight lines or something? Feels like it ought to be straight lines or something. Again, that's intuition from the graph point of view or level sets point of view or something like that, and it's absolutely not how this works. The observation I'm going to make here is that if you look at some point, x comma y, let's say that point right there, and let's think, what can we say about the field vector? And what you're going to notice pretty quickly is that these two vectors are orthogonal, right? You just easy observation. Notice the dot product 0, so they're orthogonal. And unless we're talking about the origin, which is super boring and only one point in the first place, not only are they orthogonal, they are perpendicular. So what that means is this vector that I'm trying to figure is literally perpendicular to this vector, namely the position vector for my input point. And so how would I draw a vector based at that point that's perpendicular to the green vector? Well, that's one possibility. That's the other possibility. And between these two possibilities, how do you decide? Well, pick some points and plug them in and just literally see one. You know, you only have to check like a couple points, and then you'll notice, yeah, it's always counterclockwise. Okay, and I think this is a nice exercise. I'm going to leave the details to y'all to confirm that this formula right here, it is indeed a linear transformation, and it's a linear transformation that turns the input vector a quarter turn counterclockwise. Now, this is I'm going to call this an important exercise. One thing I'm going to remind y'all of, I know but this goes way back to the very beginning of the class, right? But we are assuming that you're proficient with the fundamentals of linear algebra. And this argument here, that this linear transformation turns the input vector xy a quarter turn counterclockwise by way of this formula, is a linear algebra argument. And the way you're going to do it, broad strokes, is as follows. Remember, every linear transformation is represented by a matrix. A matrix can be understood by its columns. The columns are the images of the standard basis vectors. And if you just literally compute the images of the standard basis vectors, make those the columns, deduce the corresponding formula for the linear transformation, you'll find you get exactly this. Right, so again, nice exercise. If you get stuck on that, if you're not sure what some of that meant, come to my office hours. I would love to explain, walk you through it in careful detail, answer all your questions, right? But do make sure that you are very comfortable with that argument. We are going to assume that you're good at that kind of thing. That not only can you take a formula for a linear transformation and draw geometric conclusions about it by way of those observations, but vice versa, that if you know something geometric about a linear transformation, that you can use that to deduce the formula. Okay, so make sure you're comfortable with all of that. All right, how we doing? Pause. Everybody's all right? Whoa, to the wrong spot. Okay, here's one. This one's a weirder formula. This is the most compact way to write it, but not really, honestly, particularly the most transparent way to write it. I prefer, instead, to write this vector field like this. Now, that's clearly bulkier. Right? What's the advantage to this? And what I like about this expression here is that you can see the direction by way of that right there. Right, that's a unit vector. That's something divided by its own magnitude. Everything outside of the green here is just scalar. This is only about magnitude. Doesn't say a thing about direction. Right? And so I have literally the unit vector pointing the direction that the field vector points right there in front of me. And that's super handy. Now you'll notice that is the position vector divided by its own magnitude, and that means that is a unit vector that points, wherever you might happen to be. This is a unit vector that points radially outward. Right? That's a unit vector pointing away from the origin, just like x does. Is that good? So now the other thing you're going to notice is that the magnitude part is pretty easy to motivate. That we call that inverse square, because how that magnitude depends on distance is inverse square. Distance from the origin, that is. So altogether then, these vector fields, I hope it comes as no surprise, we call these radial inverse square vector fields, or at least that's what I like to call them. And it turns out they're super important. They're super common. You're going to see a lot of this vector field. Because radial inverse square vector fields represent, for example, electric fields. And an electric field is another physical phenomenon. It's not the flow of a fluid, right? But it is a thing which at a given point there is a direction and a magnitude, namely a vector representing what the electric field is doing at that location. So another physical phenomenon that's very naturally and kind of just kind of perfectly, frankly, represented by a vector field. So electric fields, again, kind of a big deal, right? Engineers have to understand electric fields, and this is how we represent them. By the way, likewise, gravitational fields. And you might be thinking to yourself, I have no intentions of becoming an astronaut. I do not need to understand gravitational fields. I hear you, right? But that's still not quite true. It turns out that gravitational fields and electric fields are structurally, in terms of the formula, again, both radial inverse square, they both have exactly this form. So gravitational fields represent an opportunity to gain intuition for how electric fields work. Because, say what you will about gravity and electricity, but gravity is the more relatable, right? We have everyday experience with gravity. Humanity has understood gravity reasonably. Look, not perfectly, of course, right? It was general relativity and all that stuff. But pretty much we've understood gravity for hundreds and hundreds of years and have had everyday experience with it for ever, right? And electric fields are subtle and you can't see it, and probably most people in the world don't even realize they exist, right? They're much more difficult to imagine. So the fact that you can use the much more relatable idea of gravity as a model for understanding electricity is a very nice observation, I think, a powerful little tool. And I just wanted to plant that thought. We're going to do quite a bit with that, actually, later in the course. So, heads up. All righty. Gradients. Now, we've talked about gradients before. You didn't hear me say the word vector field in any of that discussion because we didn't know what a vector field was at that time. It wouldn't have made any sense. But now I make the observation that, in fact, gradients are vector fields. How about that? This is an easy observation to make, in fact, because if you give me here's a scalar valued function, right? And if you take that scalar valued function, if you compute the gradient of it, the gradient gives you a vector. Well, wait a minute. It gives you a vector that you evaluate based on what point you're looking at. So said differently, at every point, you get an associated vector. That's a vector field. So that's just kind of a different point of view on gradients. Now notice I have drawn the graph of the function up here, kind of sitting over the gradient that I've got drawn down here. And I claim, for your consideration, that the gradient always points uphill, just like it did in Chapter 2. And you can even see that on the picture. Whatever point you might be happening to look at, let's say I look at this point right there, if I were to go up onto the graph, This direction is the direction that would have me going uphill on the graph. Let's see, I wanted to scroll. Oh, and I should be in this mode here. There we go. So yeah, the direction that the gradient points, uphill. And if you go to a different point, same deal. All of these gradient vectors point in the uphill direction for their corresponding points on the graph. Okay, again, old news. Okay, righty. Now let's talk terminology a little bit. This is point of contention. Y'all remember derivatives, right? Think back to Calc 1, ancient history, long ago. And if you take some function, you can take the derivative. The result is called the derivative. And then you can go the other way, and that's called the antiderivative. Right? Well, we already know gradients are kinds of derivatives. So I think when you take the when you take the gradient, that the resulting thing should be called the gradient of little f, in this case, whatever you're taking the gradient of. And I think, in perfect analogy, when you go the other way, when you undo, when you take a vector field and ask, what function might that be the gradient of? I think this should be called the anti-gradient. Because, I mean, my gosh, it is, right? What in the world else would anti-gradient possibly mean if not this, right? So I think it's just a self-explanatory terminology. And this is a term that's out there. This gets used here and there, but surprisingly to me, not as much as another term. And this other term I think is weirder. They call it a potential function. It's not at all clear immediately why we would call it that. Now, the reason why they call it that, right? This is not a baseless choice. Here's a fact about how potential energy and forces relate. They relate by way of gradients. An easy example to think of here is think about gravitational potential. So here we are in the vicinity of the Earth's gravitational field, right? And which direction does the force point? Down. Definition of down. Right? What's the deal with potential energy? Well, potential energy is higher as you go higher. The formula for potential energy is literally some constant times altitude. Right? Higher altitude, higher potential energy. What's the gradient of a function that's increasing as we go that way? Well, the gradient is up. The force is down, but the gradient is up. Right? So in fact, yes, it is true that the process of computing the gradient of potential energy very closely connects to force. And so, yeah, there is a natural argument to want to call what I like to call the anti-gradient, to call it the potential function. And this is by far the more common term. So you're going to hear a potential function, whether I like it or not, whether you like it or not, right? That's out there. And now you may have noticed why it is I'm uncomfortable with this terminology. Right? And that's because this minus sign right here, right? We just got through discussing that the gradient points up, but the force points down, or said differently, the anti-gradient of force isn't potential energy, it's the negative of potential energy. So to me, this is what I would call strike two for this terminology here. It ignores the little matter of a minus sign, and minus signs are important. Again, you can call it conceptually trivial, but again, we don't want the bridge to fall down, and if you forget minus signs, bridges fall down, right? So where the rubber meets the road, this kind of stuff really matters. So I don't like it for that reason. I also am a little uncomfortable with the fact that making sense out of this term, potential function, requires thinking about specifically a physical metaphor. And we're not always looking at physical examples. Not all examples are physical. Right? What if you're doing an example in economics? There's nothing physical going on there. What if you're just doing math just cause, right? There's no physical example there. So anyway, to me, I think this is unfortunate. That's a strong word. It's not my personal preference. You're going to hear me say anti-gradient. You're going to hear most other people say potential function. I just wanted you to be aware of the pros and cons of those questions. How we doing? Everybody okay? Okay. So we talked about forces, electric fields, gravitational fields, and I also mentioned at the very start of all of this that a vector field can represent the flow of a fluid, and there's lots of different kinds of fluids whose flows we might want to represent. Take your pick. Ocean currents, I think, are arguably maybe the easiest ones to think about, right? Because you don't even need to think about the ocean. Just think about a fish tank, right? If you have a little aquarium right there on your desk or whatever. I'm not saying you should do this, but you could stir up the water in there, right? The water would flow around, and at every point there would be a vector indicating what the velocity of the fluid is there, and the vector field would be how you would describe that motion of that water, right? Pretty natural. I like to point out there's other examples. The one that I think is most worthy of observation and discussion is in 2 dimensions. If you think about animal migrations, right? Now you might say to yourself right off the bat, animals are not a fluid. Animals, like if I have a herd of, zebras or whatever, right? There's a bunch of individual animals there. The herd is not a fluid. Wait a second. Air is made up of a bunch of individual little particles too, isn't it? We call that a fluid. There's a matter of scale distinguishing these 2 examples, but if you get right down to it, there's really no particular reason why we can't think of animal migrations as being the flow of a fluid. And depending on the scale you're talking about, it's actually very natural and can be a useful point of view. So anyway, for your consideration. All right. So here's a computation. I think this is a really important computation. The payoff for this is going to come when we get into chapter 6 and 7, mostly chapter 7. We're going to motivate a term here that we'll be using quite a bit. In fact, arguably that undersells it. We're going to be motivating here one of the most important objects of study in chapter 7. So here's the question. We're going to start with, suppose we have a vector field representing velocity of a fluid. So we talked about vector fields representing fluids. Specifically, the field vector is the velocity of the fluid wherever you're looking, whatever point you're putting in. Okay. All right. So what I want to do is I want to compute from that, I want to compute this thing called the flow rate. So flow rate says, suppose you have some small, and for the moment I'm going to say flat piece of surface here, like that, small flat area. And specifically, I need to talk not just about how much area there is, I need to talk about how that area is sitting in space. So if you look at my left hand here, right, my left hand is got a certain amount of area, but it's also arranged in space in a particular way. And as my hand is arranged here, very different from if I were to do like that. There's a completely different way of that area to sit in space, right? Which is also different from that, right? How your area is arranged, what we call oriented in space, depends on, well, different ways that you could describe it. You could describe it by a couple of vectors parallel to that plane that area defines, or you could use a normal vector. And this is a very common choice. Notice if you know what the unit normal vector is, that tells you exactly how your area is arranged and how it's sitting in space. Does that make sense to everybody? Okay. All right, so unit normal, like so. Okay, and again, we have a vector field representing the velocity. Oh, wrong color. We have a vector field representing the velocity of the fluid, and so let's say the fluid is flowing about like this. Notice that as I have it drawn here, the fluid is not moving perpendicular to the surface. It's moving off at some angle with the surface. And the question I want to ask again is I want to ask the question of what's the resulting flow rate? Not the velocity. Velocity is distance per unit time, right? Flow rate is volume of fluid per unit time. And I think this makes sense intuitively. If you have some area and if there is fluid flowing through that area, well, there's going to be a certain number of cubic inches of fluid that will flow through per unit time, right? And that's an interesting thing to want to talk about. So, for example, let's take a river, right? At the mouth of the river, reasonable question to ask. How fast is the water flowing if we want to be sloppy about it? And notice there's a big difference between literally what is the velocity of individual particles of water, that's in feet per second, versus, yeah, but what's the output, right? Literally how much water, cubic feet of water per second are flowing out of that river? Everybody see the difference? Flow rate and velocity. Okay, so given the velocity, how do we compute the flow rate? So here's the argument. It's ultimately not such a big deal. I make the innocent observation that in a given, oh, by the way, I should highlight here just to be clear, in a given amount of time delta t, this is literally the fluid that flows through that area in some amount of time delta t. It's going to make a little parallelepiped. And how do I compute that amount of volume? Well, it's going to be, let's see here. Ooh, I'm running out of colors again. It's going to be the what I'm going to call the height times the area. And, oh gosh, the yellow doesn't show up very well against the, let me just do like that. Height times area. The slightly yellower green is where the yellow area is. Sorry about the color choices. Everybody on board with that? Height times area of the base, right? Old formula from high school geometry. Okay, and just for visual satisfaction, I'm going to go ahead and erase the green. It's, okay. Okay, what is that height? Well, we're going to understand the height by, and I'm going to zoom in so I can see better. How am I going to understand that height? What I'm going to do is I'm going to look at this. Oh gosh, wrong. I'm going to look at this vector right there. That's what I'm going to call the D vector. Oh gosh, I'll do it like that. That's the D vector. So that D vector, notice, is basically the displacement of a particular particle of water that when I started the clock was here, and that when I stopped the clock was here. This is the displacement that a given particle of water has experienced over an amount of time delta t. So I know its velocity is the field vector, and I know the amount of time is delta t, and so altogether, back to here, and let me just write down over here on the right, that D vector is F delta t. This is just literally velocity times time. Displacement is velocity times time. So that's that D vector. And we'll come back to that in a moment. And now that we've got our hands on the D vector, I make the observation that the height, this H that we're interested in, is literally the component of the purple D vector in the normal direction. And that's what I have right here. It's the normal component of D. And now, good news, we have formulas for how to compute components. In particular, component is dot product with a unit vector, but N is a normal vector. That's a unit vector, right? By assumption, using a unit vector N. In fact, we can even see that right here. Unit vector N. Handy. Yes, we can rewrite that as that dot product. And then I'm going to plug in what we just deduced about D. D is field vector times delta T. So I plug in for D, field vector times delta T. And we're mostly done with our computation at this point. So let me just move back out. Let me clean up this mess. By the way, of course, all this is being recorded, so if you want to consider part of this argument that I'm about to erase all the color coding of, it's on the recording. You can look at it at your leisure. So let me clean up the picture. And all together, we've determined, that the volume, I'm going to be in the highlighter mode. The amount of volume in an amount of time delta T is that, or said differently, volume per unit time. Think about if I were to divide this over to the other side. Volume per unit time is this expression right here, F dot N times A. So, and this is what we call the flow rate dV dt. Everybody buy it? Yeah.
Why do we, how can we use, change in volume equals height equals area? Why is it change in volume, not just...
Oh, no, delta in this case doesn't mean change. Delta means a little piece of, right? And so what we have here is this is a differential amount of volume, differential in the sense that we're thinking about how much volume passes through in some differential amount of time, delta T. So the idea is we're thinking of delta T as being small, and we're doing linear approximations only, assuming everything's constant, and just making a simple estimate of that what we call differential amount of volume. Yeah. So it doesn't represent a change. Yeah. Okay. How we doing? Okay. All right. So this is actually a really important thing, as it turns out. So when certain expressions or objects or whatever you encounter of mathematical interest that turns out to be the answer to a really natural question, and that's going to come up again, it's natural to develop a notation and a terminology. And the terminology is that we call this flux, right? This expression flux means F dot N times A. Now, if you're talking about a fluid, then flux means flow rate. Yeah, sure. But we might be talking about another vector field that maybe isn't a fluid, where nothing's flowing at all. And flux is still interesting, even though I can't call it flow rate. Okay. And the terminology that we use is, the notation that we use is this right here. It's the capital Greek letter phi, which I am sure they chose because it starts with the same F sound as flux. If not, it's certainly a nice way to remember it. Okay. All right. How we doing? Is everybody okay with the terminology there? Now, I'm going to give you all another exercise, and again, I think this is a fantastic exercise, very educational opportunity, and that is to consider a different scenario with a different question and what you're going to find is that in a very closely related but importantly different scenario, asking a very closely related but importantly different question, amazingly you get the same answer. So if instead of the vector field representing velocity, what if instead the vector field represents density times velocity? Seems like a weird thing to do, right? Why would we care about density times velocity? Well, here's an example for your consideration. Let's go back to zebras, right? Got a bunch of zebras walking around. If you're interested in how many zebras per minute are crossing some line or whatever, right? How fast they are walking is not the only question, right? It's just not. Because if there's a low density of zebras, then as they walk, not that many zebras are crossing your line. But if there's a very high density of zebras walking the same exact speed, then there's a lot of zebras crossing your line, right? So the density actually does naturally fit in. It really does make a lot of sense to think about. If you're interested in quantity of fluid, not volume of fluid, but actual how much fluid, factoring in the density really does make sense. So that's how we're adjusting the premise, or the way we're representing things. And we're also going to ask a different question. Instead of asking volume per unit time, we are instead going to ask what is the mass per unit time. Again, arguably more natural question, right? I'm usually interested in how many zebras, literally, not how much space are those zebras taking up, right? So, much more natural question, right? A more natural way to represent a fluid flow, and a more natural question to ask about how much is passing through. And what it's going to turn out to be, that the answer, again, is the same exact expression. It's F dot N times A, as it turns out. And so again, flux. Same expression, same notation, same terminology. Flux, again, is the answer to this natural question. Okay, so this is an exercise for y'all to do on your own. I'm going to show you approximately how to do it. Again, come to my office hours if you have any questions, if you get stuck, whatever. Basically, the idea is you're going to do almost exactly the same thing here, except instead of literally computing the volume that passes in a certain amount of time, you're going to compute instead the mass. And of course, the difference, if you make that mass, is that you need density times velocity, which means you're going to have an extra factor of density over here. And that's just going to carry through the calculation, and then at the very end, that density is going to get absorbed in to the vector field, because after all, it is part of the vector field. Right there. So that's the broad strokes. Everything else in the argument is almost exactly the same. Right? So this is a good exercise in extending this argument we just made, and it's a good exercise to make sure that you're really following this argument that we just made. So very healthy. I hope y'all will give that a shot. Again, come talk to me in office hours if you get stuck or have questions or what have you. Okay, real quick, by the way, most of this page we're not going to make officially part of this course, so I'm about to scratch off most of this page in just a moment. But I do want you to be aware of this because it is a confusing situation. There are some weird fluids out there. Very strange fluids out there. We think of fluids as being stuff like air and water. Maybe you've even opened your mind to the idea of zebras, right? Okay, here's one that's fundamentally different. Light. Now, not a shocking first thought. If you think about it, if there's a light bulb somewhere, it's shooting out a bunch of photons. That's kind of like a fluid in a way, right? Here's what's really weird. If you have two zebras, they cannot pass through each other, right? like that. If you have a bunch of water, you cannot have a flow of water going this way and a flow of water going that way that they just pass through each other. No, they collide, and in some form or another, ultimately they have to find a way to kind of go along with each other. Ditto the zebras. As easily observable, you look at any stampede of zebras, right? And the two zebras right next to each other pretty much going along with each other. Okay. Light is not like that. And so, for example, if we look at here, if I have a green light bulb right there, it's shooting out photons. Well, at a given point, way over here, there's going to be a green velocity of a photon that came from this bulb that happens to be right here at that particular moment. Okay, yeah, but if you have a blue light bulb over here, right, and it is shooting out photons every which way, well, then when you get over to that same point, there's going to be a blue photon that came out of this blue light bulb, which happens to be, at the same place at that same particular moment. And so looking at this question, looking at this scenario right here, pretty reasonable question to ask. What velocity would I attribute at this point? I've got two different velocities. Or even density times velocity. They're going to be different at this single point. So I can't basically, I just can't do that. This idea that we're going to represent the flow of photons by velocities or density times, it just doesn't work. And by the way, you don't need this is not a obscure lab conditions only kind of phenomenon. I'm saying this is happening in this room right now, right? That light bulb and that light bulb are shooting out photons that are coming right there at this point, right here, right this particular second. There are photons coming from over there, and there are photons coming from over there. Right? And more. I mean, there's a bunch of hot spots all over this screen that are all shooting out photons that are coming to this same point. So this is the natural state of affairs of the flow of the fluid of light. So what do you do? How do you represent light flow with a vector field? And the answer is that you look at the answer to the question that we've already got, right? And you turn it around backwards. So what we've previously done is presumed that we knew a vector field representing, density times velocity in this case, whatever. And then you asked, given that vector field, we asked, what is the flow rate? And we're going to turn that around backwards by saying, look, for any given flat little piece of area, I can empirically determine the flow rate. You can just measure what the flow rate is. And then I'm going to ask, what vector field, by way of this formula, would have given me that same answer? And it turns out that there's always a vector field that will do this for whatever flat area you're looking at. It's a single vector field representing the flow of light, let's say in this room, that would do this. And so anyway, I just wanted y'all to be aware that there is this nasty little situation, and there is a clever answer for how to deal with it. Yes?
It's just pretty much like a more generalized version of Gauss's law.
Gauss's law comes out of this idea, yeah, but there's a lot that goes into this. Yeah, that's a big leap. Yeah, absolutely. Okay, so now on this page, there's an example that follows, and this again is where I'm sad to say, tough choices and all that, and we just don't have time. That's a lovely example. I really like it, and it makes me sad, but I am going to have to draw a big X through this. So not only are we not going to spend class time on this, you're not responsible for this, okay? But if you're looking for a cool example, this is a great example of of how you can make very clever arguments and come up with really powerful conclusions that would have otherwise been very difficult to come through. So anyway, it makes me sad. Oh well, life's disappointing. Okay, let's see. We are about out of time, it looks like. Let me just check the thing. Yeah, we got 20 seconds left. I'm sure I owe you 20 seconds. Who will draw the line right there. See y'all later. Have a good one. See you on Friday.